In this video, we're going to learn how to solve systems of three linear equations that depend on three variables. To get a sense of what systems of three equations are about, let's take a look at a problem. Suppose that a fruit stand sells apples, bananas, and oranges for $1, 25 cents, and 75 cents respectively. If it sold 90 pieces of fruit in total, and if it sold twice as many bananas as apples and oranges combined, and if it made $40 in sales, then how many pieces of each fruit were sold? This is probably not the kind of problem that you can quickly solve in your head. But as is so often the case in mathematics, we can begin to understand what's going on here by giving names to the things that we don't know. And here there are, of course, three unknowns. One of them is the number of apples sold. Let's call that x. Another is the number of bananas sold. Let's call that y. And finally, we have the number of oranges sold. Let's call that z. Now that we've given names to these unknowns, we can begin to describe the mathematical relationships among them. So let's think about it. If 90 pieces of fruit were sold in total, then it means that the number of apples plus the number of bananas plus the number of oranges sold must add up to 90. How much money was made? Well, it was $1 per apple plus 25 cents per banana plus 75 cents per orange. And we're told that sales totaled $40. Finally, we're also told that the number of bananas sold was double the number of apples and oranges sold combined. So y is equal to 2 times x plus z. And what we've just written down here is a system of three linear equations in three unknowns. It turns out that if all three of these equations are going to be true, then it must be the case that the fruit stand sold 10 apples, 60 bananas, and 20 oranges, a fact that you can quickly verify for yourself. But how on earth would you solve a system like this if you didn't already know the answer? How, that is to say, does one actually solve a system of three linear equations? First, we're going to step back and carefully define exactly what we intend to study. By definition, we will say that a system of three linear equations in three variables is a set of equations that takes the form shown on the screen. Notice that this system is a collection of exactly three equations, and that there are three variables or unknowns here, commonly denoted x, y, and z. All of the coefficients in blue are just fixed constants. And when we talk about the solution of a system of equations in three variables x, y, and z, what we will mean is all triples of numbers, x, y, z, which have the property that when they're substituted into any one of the equations in the system, they make that equation true. Let's now ponder an abstract question. How many solutions can a system of three linear equations in three variables have? To get a handle on this question, one important thing to understand is that a linear equation in three variables actually corresponds to a plane in three-dimensional space, just as a linear equation in two variables corresponds to a line in two-dimensional space. Three linear equations in three variables would therefore correspond to three different planes situated in three-dimensional space, and the solution of those three equations would be precisely where those three planes intersect. It then only remains to imagine how these three planes might be situated in space. And one example is shown on the screen. Notice that the red, white, and blue planes here actually intersect at a single point. x, comma, y, comma, z in three-dimensional space. And so the three linear equations that correspond to these three planes would actually represent a system that has a single solution. But here's another possibility. Suppose that the three planes that correspond to our three linear equations are oriented as shown. Then they would actually intersect at a line in three-dimensional space. And it would follow that the system of equations represented by these three planes has infinitely many solutions, which correspond to all of the infinitely many points on this line of intersection. Yet another possibility emerges when we consider that our three different planes might be parallel to one another. In that case, they wouldn't intersect at all, and our system of equations would have no solutions. Now, there are in fact other ways in which three planes can be situated in three-dimensional space, and you might enjoy thinking about what other configurations there can be. The key idea to take away, however, is that three planes could intersect not at all. They could intersect at a single point. They could intersect at a line, or they could even intersect at a plane if all three equations actually represent the same plane. And so a system of three linear equations could have no solutions, a unique solution, or infinitely many solutions, just as with systems of two equations. Now let's get to the business of actually solving a system of three equations. We're going to do an example problem that asks us to solve the system of equations shown on the screen. And the key idea will be this. We're going to take this system of three linear equations and reduce it to a system of two linear equations, which we already understand how to solve. Here's the idea. We're going to begin by considering only the first two equations in our system, and then we'll make the following observation. If we add these equations together by adding the left-hand sides and the right-hand sides together, then we end up with a new equation that is true as long as these two equations in our system are true. And moreover, that new equation will not contain the variable x. So watch, when we add the x terms together, we just get 0. When we add the y terms together, we get negative 2y plus 3y, that's just y. When we add the z terms together, we get 3z minus z, that's 2z. And then, adding the right-hand side together, we get 9 plus negative 6, which is 3. Now let's take a look at the second two equations in our system. This time, adding them together does not eliminate the variable x, but there is something we can do to make sure that x does get eliminated. See if you can figure out what that is. We can notice that we are free to multiply both sides of the second equation by the number 2. And if we do that, then the coefficient of x in the second equation will be negative 2, which will perfectly cancel the positive 2 in the third equation. So when we now add these two equations together, we obtain the following. The x terms, as we've said, cancel. Adding the y terms together gives us 2 times 3y minus 5y, that's just y. Adding the z terms together gives us 2 times negative z plus 5z, that's plus 3z. And adding the right-hand side together gives us 2 times negative 6, that's negative 12, plus 17, which is 5. Notice how our original system of three linear equations in three variables has now been reduced to a system of two linear equations in two variables, which we can solve using known techniques. We can solve the first equation in our two-variable system for y to obtain y equals 3 minus 2z, and then substitute that in for the y in the second equation. That gives us 3 minus 2z plus 3z equals 5. This in turn means that z plus 3 equals 5, or in other words, that z equals 2. And if z equals 2 and y equals 3 minus 2z, then that must mean that y is equal to 3 minus 2 times 2, which is negative 1. Finally, we can go back to any one of the equations in our original system and substitute y equals negative 1 and z equals 2 into it in order to solve for x. So looking at the first equation in our system shows us that x minus 2 times negative 1 plus 3 times 2 must equal 9. And if we quickly solve for x, we see that x must equal 1. And so we've shown that our system has a unique solution. It's the point x equals 1, y equals negative 1, and z equals 2. And it's a nice exercise to check for yourself that when you substitute x equals 1, y equals negative 1, and z equals 2 into any one of our three original equations, it will make each of those equations true. To recap, the strategy for solving a system of three linear equations is to select two of those equations, and then, possibly after multiplying one or both of them by a convenient non-zero number, add them together to eliminate a variable. You could choose to eliminate the variable x, but it could also be y or z. Next, choose a second set of two equations from the system, and likewise add them together to eliminate the same exact variable that you eliminated in step 1. Then you will have a new system of two equations and two unknowns, which you can quickly solve. And then by substituting everything back into the original system, you will obtain x, y, and z. But hang on a minute. What if the three equations in our system correspond to three planes that intersect at a line? What if our system has infinitely many solutions and we want to describe all of them? What should we do then? Let's have a look at a different system of three linear equations and try to solve it by reducing it to a system of two equations and two variables. One thing we noticed right away is that the middle equation, 2x plus 3z equals 1, already has the variable y eliminated, so we can simply write it down. Next, we can turn our attention to the first and third equations and try to eliminate the variable y from those. And the clearer way to proceed here is by multiplying the first equation by negative 1 and adding it to the third. That gives us, let's write it down, negative x plus 3x, which is 2x, then negative y plus y, which is 0, negative z plus 4z, which is 3z, and on the right-hand side, negative 2 plus 3, which is 1. And right away, we realize that the system of two equations that we've derived from our system of three equations actually repeats an equation. That system has infinitely many solutions. What we can now do is simply solve for one of the two remaining variables in terms of the other. So for example, solving for z would give us z equals 1/3 minus 2/3 x. This shows that z depends on x. If we assign a value to x, we can also assign a unique value to z. Now, we can take this expression for z and substitute it into either the first or the third equation in our system and solve for y in terms of x as well. That gives us y equals 5/3 minus 1/3 x. X here is a kind of parameter or free variable, and once we know what x is, we also know what y and z are. To write down the full set of solutions of our system, we now reason like this. The variable x can be any real number, but once we have x, we know that y must be 5/3 minus 1/3 x, and we know that z must be 1/3 minus 2/3 x. And so this order triple that we've just written down actually describes all infinitely many solutions of our original system of equations. And what's important to understand here, once again, is that x is a free variable that can be any real number whatsoever. And as we let x vary, this order triple of points actually traces out a line in three-dimensional space that corresponds to the intersection of all three planes determined by our original equations. This is how we can describe the full set of solutions of the original system.